Hi everybody, this video is the first of two videos that goes over section 4 of chapter 3, and here we are going to be talking about the present value of an annuity. Specifically, yep, you guessed it, we're going to be talking about the present value of an annuity. Then we are going to talk about this thing called amortization, which is basically the idea of looking at the present value of an annuity from the perspective of a loan. And then in the follow-on video, we will talk about amortization schedules, which you will get to work on in an assignment. And it's also the kind of schedule that you will receive whenever you actually take out a mortgage on a house or a long-term loan. And we will conclude in that video with some applications, which, yes, will include problems dealing with mortgages on houses, which is something that we will all have to deal with. Suppose you have access to an account that pays 8% annual interest compounded semi-annually. And suppose you want to withdraw from this account $2,000 every 6 months for the next 3 years. Question is, how much should you deposit now into that account so that can happen? Well, that amount of money that you need to deposit now is the present value of the six $2,000 semi-annual payments. And we can actually find this present value for each withdrawal using the compound interest equation. All we have to do is rearrange it so that we are solving for P, which is the present value. And if we do, it will look like this, where A is the future value for each of the payments, and then N is the duration of each particular payment. Okay, so what is this going to look like? Well, once again, this is our equation. N will be their payment number, which will be either or withdrawal number, which will be 1 through 6, and I, which is the interest rate over the compounding period, which once again it is semi-annually, so there are 2 compounding periods per year, is our annual interest rate divided by 2, since we have 2 payments per year, and that gives us 0.04. And this is pretty much how this works. Now, our first payment, which will occur 6 months after our deposit, we will want to take out $2,000. The question is, how much should we put in now so that we will have $2,000 in 6 months? And this would be the answer. This is how much you would need to put in. Notice that I took this to the 3rd decimal place, and I wanted to do that to minimize any potential rounding errors. Okay, the second payment, which occurs will occur from a year from now. And how much do you need to put in or to deposit now to make sure you have $2,000 to withdraw in 1 year? That is right. There it is right there, $1,849.11.2. And we continue on. Our third payment, a year and a half from now, to make sure that happens, we would need to deposit $1,777 now. If you wanted to withdraw $2,000 in 2.5 years, $1,643. And if you wanted to withdraw $2,000 in 3 years on your final payment, you would need to deposit $1,580.62. Now, if you added all this up, this means that you would need to deposit $10,484.27 now, so this account can produce for you $2,000 in 6 months, 1 year, year and a half, all the way down to 3 years, and you will have absolutely nothing in the account once you've taken out your last payment. So if we make an initial deposit of $10,484.27, we can withdraw $2,000 every 6 months, and we will have a balance of 0 after our last withdrawal. So we can say that a present value of an annuity that makes semi-annual payments of $2,000 at 8% interest compounded for 3 years is $10,484.27. Another way to compute the present value of an annuity is through the use of this formula. And we're not going to talk about how to derive it. We're just going to talk about how to use it. And this brings us to our first theorem. It turns out that the present value of an ordinary annuity, we're going to call that PV, is equal to the payment times 1 minus 1 plus the interest rate over the payment period raised to the negative n power, which is the number of payment periods, divided by I. This is the equation that we want to use whenever we have a present value scenario, or whenever we have a scenario that involves a loan and equal periodic payments to pay it off. Now, one of the things that we do want to point out is to remind you how to compute I and how to compute N. Remember, the interest rate over the payment period is always going to be equal to the annual interest rate, which is R as a decimal, divided by the compounding period. Furthermore, the number of payment periods is going to be equal to the compounding period, the number of compounding payments made over the year, times the time duration of the loan in years. So we always want to remember that. And this brings us to our first example, where we need to compute I and we need to compute N. Now recall that I is equal to R as a decimal divided by M, which is our compounding frequency, and N is equal to M times time in year. And once again, M is our compounding frequency. Notice that for computing I and M, you only need R, you only need T, and you only need M. You don't need to worry about the payments. The payments have nothing to do with the problem. Okay, so for the first problem, we have a loan for 12 years, that's T, at 9.9% interest, that is R, the annual interest rate, and we're compounding semi-annually, which implies that M is equal to 2. Now recall that we cannot work with R as a percentage. We need to write that as a decimal, and that would be 9.9% divided by 100. So the decimal version of R would be 0.099. And with that, we can figure out what I is. I will be 0.099 divided by 2, which will give us 0.0495, and then N, which is going to be M, which is 2, times T, which is 12, is equal to 24. So there you go. That's the first problem. Now in the second problem, we have that T is equal to 6, and R is equal to 8.24%. We can't work with percentages. We're going to divide that by 100, and that gives us that R is equal to 0.0824. Now we are compounding quarterly, and that means that M is equal to 4. Okay, so I is going to be our annual interest rate, which is 0.0824 divided by M, which is 4. And that will give us 0.0206. Okay, and then N is going to be equal to our compounding frequency, which is 4, times the duration of the loan, which is 6, which once again is 24. And then finally, here we have monthly payments made for 3 years, so T is equal to 3. To repay a loan where the annual rate is 10.8%, which as a decimal divided by 100 would be 0.108, and we are compounding monthly, so M is equal to 12. So for I, we will have 0.108 divided by our compounding frequency, which is 12, and that will give us 0.009. It's kind of interesting. And then N is going to be equal to M, which is 12, times T, which is 3, and that will give us 36. There you go. And that's pretty much how you would do your first 4 homework problems. Example 2 is will give you practice for using the present value formula. What you'll notice is that we're going to use example 2 to find the present value for NA, the payment for B, N for C, and I for D. And to do that, since this is going to require a little work, we're going to use a different form of our screen to make that happen. Now for part A, we are given I, we're given our payment, and we're given N, so that is pretty straightforward. And what we will have is that our present value is going to be equal to our payment, which is $238, times 1 minus 1 plus I, which is 0.039, raised to the negative n power, which is negative 21, all over 0.039. Now we can do some simplification here. First thing that we can do is combine this, and if we do, we will have 238 times 1 minus 1.039 raised to the negative 21, all divided by 0.039. And now we need to compute this on our calculator. Let me clean this one up just a tad. There we go. And how can we do this? Well, here's our calculator over here. What we can do is basically write it exactly as it's written. Now remember here, this kind of, since we have a fraction here, that kind of applies a grouping symbol right there. So we can do 238, actually let me clear all this. 238 times parenthesis 1 minus 1.039, there we go. We can use this for our exponent. Now for our negative sign, we need to use this button down here, negative 21. We can use this cursor to get out of it, and then, or use this button to get out of the exponent part, and then close the parenthesis, divided by 0.039. And that is our present value. That tells us that the present value is equal to $3,369.902. Now we probably want this in dollars and cents, and the third digit is less than 5. So this will round to $3,369.90. Okay, so that's part A. Let's take a look at part B, and before we do that, let me change colors real quick. So once again, we're going to have the exact same equation, but notice that this time we are looking at, where's part B? There it is. We need to find the payment. So making our substitutions, we have $29,380 for our present value. So PV is 29380. That's going to be equal to our payment times 1 minus 1 plus I is 0.012, 0.012. All that is going to be raised to the negative 96 power, divided by 0.012. Now recall, payment's what we're looking for, so we actually need to rearrange this equation so that we have payment all by itself and all the numbers over here. The first thing that we can do is we can multiply both sides by 0.012. So times 0.012 here, and then times 0.012 there. I should have given myself a little more space. And if we do, this will cancel there, and that will multiply out to 1. And then we will have 0.012 times 29,380 is equal to our payment. Now remember, since we have this fraction here, that implies grouping symbol, so now we probably need to add parentheses. 1 minus, and this we can combine, that's just going to be 1.012 raised to the negative 96 power. Okay, now we can divide both sides by this quantity. We can divide the right side by 1 minus 1.012 raised to the negative 96 power, and we can divide this side by 1 minus 1.012 raised to the negative 96 power. And if I do, these cancel. And what I have is payment on one side. I'm going to switch sides on you. And over here, I have 0.012, 29,380, all divided by 1 minus 1.0122, not 9. Let me fix that. 2 raised to the negative 96 power. And that we can use our calculator to figure out. Now, the best way to probably do that is to first compute the numerator, then compute the denominator, and then combine the two. And let me show you exactly what I mean. I'm going to go ahead and compute the numerator first. 0.012 times 29380. Okay, that's what the numerator is. And then for the denominator, we have 1 minus 1.012. We're going to raise that to the negative 96 power, and that's our value for the denominator. Now we can use the history and these cursors to do the division. I can go up and highlight the numerator, highlight it, hit enter, there it is. Hit divide, then I can go and highlight the denominator, hit enter, that brings it down, and now I can hit enter again, and that is my answer. And what do I have? I have $517.085. Now, since the third decimal place is 5 or greater, this will round to $517.09. Okay, and that brings us to problem C. Here, we want to find N, this sucker up here. And we have that PV is equal to 10,000, I is equal to 0.005, and our payment is equal to 250. So let's go ahead and put those numbers in. So for PV, we have 10,000. Our payment is equal to 250. That's going to be equal to 1 minus the quantity 1 plus 0.005 raised to the negative n power all over 0.005. And let me move that over just a little bit. There we go. Okay, good. Okay, now the next thing that we can do is we can multiply both sides by 0.005. 0.005, 0.005. Also notice I have a 250 in the numerator. I can divide both sides by 250. Notice on the right hand side, this 0.005 cancels out that 0.005. This 250 cancels out that 250. And all I have over here is 1 minus, I could combine this, 1.005 raised to the negative n power. Now we can now use our calculator to figure that out. That is going to be 0.005 times 1,000, 10,000, divided by 250. And that is 0.2. Okay, I can subtract 1 from both sides. And if I do, I will have negative 0.8 is equal, these cancel, negative 1.005 raised to the negative n power. Okay, I can also get rid of the minus signs by multiplying both sides by negative 1. And if I do, I will have 0.8 is equal to 1.005 raised to the negative n power. And that was actually important because I want to take the logarithm of both sides. So with that in mind, let me move this over a little bit. And I cannot take the logarithm of negative numbers, but if I actually made them all, if I multiply everything by -1, they'll be all positive, and I can take logs. So, and that's what I'm going to do now. I'm going to take the logarithm of both sides. I'm going to take the log of 0.8, and that's going to be equal to the log of 1.005 raised to the negative n power. Okay, I can then use the power property, and if I do, I will have that the common log of 0.8 is equal to negative n times the common log of 1.005. And now I can solve for n by dividing both sides by negative log of 1.005. Okay, and then the negatives cancel, the logs cancel, and I have that n is equal to negative log of 0.8 divided by the log of 1.005. Okay, so let's see what happens here. Going to our calculator, we have log, I forgot something, clear, negative log 0.8 close divided by log 1.005. And that gives me a value of 44.7. Now we want n to be an integer because it is the number of payments, and since our decimal place is at 7, we are going to round up, and we will round n up to 45. Okay, and that brings us to our very last part, which is this one right here. What I'm going to do is I'm going to move this down so that we can see it. Okay, and here we are. Here now we want to find I. We have PV, we have N, we have the payment, but we have no idea what I is. That's what we need to figure out. So let's go ahead and do the substitutions. We have that the present value is $12,000. That's going to be equal to the payment, which is $500, times 1 minus the quantity 1 plus I, raised to the negative 60, divided by I. Now there is no analytical way to actually isolate I by itself, so we're actually going to have to use a numerical technique to solve this. And your TI-84 calculator actually has a means by which to do that. It actually has what we call a numeric solver. And the way we can find that is by going to math. And it turns out that it is the last one on the list, so you can either go all the way down or you can just go up. There it is. And then hit enter. Okay, now what we're going to do is put one expression on one side of the equal sign here and the other expression here. So on the first one, E1, we're going to put in 12,000. And now on the second one, we're going to put in this expression right here. So that is 500. Now we're going to use parentheses here, times parenthesis 1 minus, now parenthesis again, 1 plus, and then since I is our unknown variable, we want to click up here. This is our variable. Well, first I need to change that to a plus. Close the parenthesis. Exponent negative 60. Get out of the exponent. Well, that's not what I wanted to do. Get out of the exponent. Close the parenthesis, and now divided by. And then we're going to use our variable again. And now we can hit, and on your calculator, this right here will be over graph. We can just go ahead and hit graph. Okay, now we need to put in our guess for x, and how about if we put in 0.05? And then our bounds is going to look anywhere between on the entire real line to find it, and then we can just go over here and click solve. And this is our answer. Now, if we want to take the answer to 4 decimal places, we would have that I is equal to 0.0369. Our 5th decimal place would be 3, which means that we do not need to round up. So we would have 0.0369. And that's how you would solve part D. You would actually need to use your calculator to solve it for you because there's no analytic way to do it. And this brings us to example 3. American General offers a 14-year annuity with a guaranteed rate of 9.29% compounded annually. And the question is, how much should you pay for one of these annuities if you want to receive payments of $17,000 annually over the 14-year period? So this is, once again, the use of the present value annuity formula. Specifically, and that formula is that the present value is equal to your payment times 1 minus the quantity 1 plus I raised to the negative n power divided by I, where I is equal to R over M. R is your interest annual rate as a decimal. N is equal to M times T. Now, T is for this. We have a 14-year annuity, so T is equal to 14. Our interest rate is 9.29%, so R is equal to 9.29%. We can't work with percentages, we can only work with decimals. So this will be equal to 0.0929. We want to receive payments of $1,700, so our payment, PMT, is equal to $1,700. And since we are compounding annually, M is equal to 1. That makes things kind of convenient. That means that I is going to be equal to 0.0929 divided by 1, or just 0.0929. N is going to be equal to 1 times 14, or just 14. So we have our payment, we have I, we have N, we can compute the present value. The present value is going to be equal to the payment, $1,700, times 1 minus 1 plus I, which would be 1 plus 0.0929, or 1.0929 raised to the negative n, which is 14, all divided by 0.0929. And this is what you need to compute on your calculator. To do that, we need to first, we'll get out of this, and the way you can do that is by sitting second and then quit, which is right above mode. Brings us back to here. Let's clear all this. To do that, we could pretty much just write this in the way that we see it. That would be 1700, my apologies, times, parenthesis, 1 minus 1.0929 raised to the negative 14th power, get out of the exponent, close the parenthesis, divided by 0.929. That's not right. That should be 0.0929. Hit enter, and that is our answer. So let's go ahead and write that down. That will be $13,023.216. Since the third decimal place is greater than 5, this will round to $13,023.22. That would be our answer. Okay, now for the next few minutes, we're going to go back to our slides and then come back to do our final example. And here we're going to talk about amortization, or amortization. The present value of annuity is useful for assessing loans. Let's suppose that you want to borrow $10,000, and let's suppose we're going to pay the loan back in 48 equal monthly payments at 12% compounded monthly. Well, if that's the case, then the bank just purchased an annuity from us. The bank is going to pay you $10,000, and then they're going to make monthly withdrawals, or we're going to make monthly payments of whatever the amount needs to be at 12% compounded monthly. And the question is, what should that payment be? Well, this is called amortizing the debt. This means that the debt is retired or paid off in a specific length of time by equal periodic payments that include compound interest. And this is the formula. As you can see, it's nothing more than the present value formula manipulated so that we are solving for the payment. So basically, any loan which is paid off in equal payments can be assessed using the present value formula. And our next example actually uses this formula. Okay, here we are back into our OneNote calculator setup, and this is our last example for this particular video. So suppose that you want to buy a computer directly from the manufacturer for $2,317, and you agree to repay it in 48 equal installments at 1.52% interest per month on the unpaid balance. The first question is, what are the monthly payments? Okay, well, to do that, we need to use the amortization formula. Here it is right here. Our present value is right here. It's $2,317. Notice here we have 48 equal installments or equal payments. So that basically tells us that n is equal to 48. We don't need to figure that out. That's kind of convenient. And notice here they're telling us that this is the interest rate per month, and we're making monthly payments. So this is I. I is equal to 1.52%, but we can't work with percentages, so we're going to divide this by 100, and this will give us that I is equal to 0.0152, which is the decimal equivalent. So now we have everything that we need to actually solve the problem. We have PV, we have N, we have I, and we can do our substitutions. So our payment, monthly payment, is going to be equal to $23.17 times I, which is 0.0152, divided by 1 minus 1 plus I, which is just 1.0152, raised to the negative n power, which is negative 48. And we just need to compute this with our calculator. And once again, I'm going to compute the numerator, then the denominator, and then divide the two using the history feature of the TI-84. So the numerator, we have 2317 times 0.0152. There we go. For the denominator, we have 1 minus 1.0152 raised to the negative 48 power. And that's what we get there. Okay, now to figure out our payment, we highlight the numerator, bring it down, divide it by, highlight the denominator, bring it down, and then hit enter, and that is our payment. So our payment is $68.352. Notice that the third decimal place is a 2, so we don't need to round up. So this will approximate to $68.35. Okay, awesome. Okay, the last thing we need to do is figure out what the interest is. Now, the interest, in terms of a loan, is always going to be equal to the total, the amount you pay minus the amount received. Well, the amount you received is the present value of the loan. That's how much you were given, $23.17. Now, the amount that you paid was your payment times the number of times you've made that payment, which in this case is 48. So the interest rate is going to be 48 times your payment, which is $68.35. You made 48 payments of $68.35 minus the amount you received, which was $23.17. And we can compute that easily in our calculator. That is 48 times 68.35. Oh, I think I hit the wrong button there. There we go. 68.35 minus 23.17. And that tells us that our interest, that the interest that we paid, is $963.80. That's how much we had to pay for the privilege of borrowing $2,317. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.